I would like now to explain to you what is the divergence theorem, which is a very important theorem in mathematics but also in physics. I will try to prove the theorem to you by using some intuition, some physical intuition, but we will not resort to any kind of physics, even though it has so many applications that I don't even know how to count them. This theorem is called the divergence theorem, but it also goes by other names like the Ostrogradsky's theorem, Gauss-Green theorem, or even Gauss theorem. It considers a surface, any kind of surface, but it has to be a closed one, so it can be a sphere, but it can also have any kind of geometrical shape. It can be any kind of shape, and the important thing is that this surface encloses a volume. We will indicate the volume by the letter V. In addition to the volume, the theorem considers a field. So what is a field? A vector field. You can think of it as a vector f with three components in space: fx, fy, and fz. It depends on also the points at which we compute the field. For instance, if this is a point x, y, z, the field can be like this. If this is another point, the field can be different from this one. For every point in space, we associate a vector. Fx of x, y, z, fy of x, y, z, fz of x, y, z. So it is a vector with three components, but the three components can depend on the points in space. So what does the theorem tell us? It tells us that in general, if we compute a surface integral, and I will indicate it with this symbol because the surface is closed, so we'll put this circle in the integral sign, the surface integral over the boundary, this symbol in this case indicates the boundary of the volume. The boundary of the volume is the surface which encloses the volume. The integral of f, the vector field, dot product with the unit normal to the surface times the element of the surface ds. This can be converted to a triple integral in general, which I will indicate just with one integral sign, over the volume enclosed by this surface of the divergence of f times the element of the volume. In this case, this is just, if you want, dx, dy, dz. So what is the divergence? The divergence is defined as the dot product between the gradient, so it's the derivative with respect to x, derivative with respect to y, derivative with respect to z, dot fx, fy, fz, and this is equal to, it's a scalar, dfx over dx plus dfy over dy plus dfz over dz. Some other times, instead of using this notation, this symbol, it is written like this, divergence of f. I don't really like this notation, but it is often used in books. Now, let's try to prove this statement by using some intuition, some mathematical intuition and physical intuition, not just mathematical rigor. I don't want to be mathematically rigorous. I want to convey the meanings behind things so that you can reason yourself. We will consider an infinitesimally small volume, which is given by a small cube, which I will draw here. Let's consider this point to be x, y, z. This point, for instance, will be x plus dx, y, z, and so on and so forth. So this line here has a length dx, whereas this one is a length dz, and this one has a length dy. So the volume of this small cube is dx, dy, dz. Now we will consider this formula here, right here, the left hand side of this expression, and we will take as the boundary of the volume this cube. So we will try to evaluate this expression for this very small volume. For instance, over the face of this very small element, there acts the vector fy calculated at some point here. We will write down what kind of point that is. On this face right here, we have fy of x, y, z. And since the surface is infinitesimally small, this point is almost equal to the surface itself. So the surface is almost equal to the point, because it's very, very small. If I consider this surface right here, I can evaluate fy at the point x, y, z, because this point is almost equal to the surface. Okay, so this is not rigorous, as I said. In general, it could be like x plus dx over 2. These 2 points have the same y component, but the z component could be z plus dz over 2. But that's not important because it's very, very small. So in the limit, as dz goes to 0 and dx goes to 0, we get f of x, y, z. Fy goes along y, so this is the jth component of the vector f. We are considering the jth component because the components can be considered separately, because they are independent. In here, for instance, we could have fz of x, y, z plus dz. We would also have here fz of x, y, z, and so on and so forth. But we will consider in this case the y component, and then we will extend the reasoning to the other two components. In this case here, fy must be computed at the point x, But we cannot put y here. We have to insert something different, because from this point to this point there is a translation along y, so we need to consider this coordinate to be y plus dy, because the distance between these 2 points is dy. And then z. We also should consider the unit normal to the surface, which is usually taken to be pointing outwards of the surface, so this is the normal n to this surface right here. And then we have unit normal to this surface is pointing outwards, so this is n on this surface. And the integral that we have to perform is a sum. We have to integrate over the surface, but since the surface is infinitesimally small, for instance in this case over this surface we have fy x y plus dy z. This is also multiplied by j because it's a vector along j, so we have j dot n. J dot n in this case is just equal to 1 because j is equal to n, and n has length 1. It's a unit vector, so this is equal to 1 times the surface, which is this is dx, this is dz, so it's dx times dz. We should integrate this over this surface, but as I said, this is infinitesimally small, so the integral is just equivalent to this expression. But we should also consider the fact that there is this other part of the surface, so we should also integrate over this. So we should add fy of x, y, z times j dot n, but in this case, take a look. J goes inwards, n goes outwards. So j dot n gives me minus 1, because remember, the dot product is also equal to the norm of the two vectors, but they are unit vectors, so this gives me 1 times the cosine of the angle in between. The angle between the two vectors is 180 degrees, or if you want, pi. So this is equal to minus 1. So we have minus sign here. And then we should also multiply by the same thing, because the area is the same of these two faces. So it's dx dz. And this is equal to fy of x, y plus dy z, and then we have minus fy of x, y, z times dx dz. Now take a look at this. This expression is very similar to the definition of derivative. If we divide this by dy and multiply obviously by dy, we get the same expression, right? But what is this? This is just the derivative of fy calculated at the point x, y, z with respect to y. So this is equal to dfy over dy times the element of the volume, which is dv. So in general, if we consider the other two directions, we will get something very similar. And you can understand that if we integrate over this very small surface, f dot n ds over this very small surface is just equal to the divergence, because we have dfy over dy plus dfz over dz plus dfx over dx. So this is the divergence of f times the element of the volume over this very small surface. And then how can we extend this to a general surface? Well, the idea is not so complicated. Let's consider another step in which we have two very small surfaces very close to each other. For instance, this one, and then we have this one. Okay? What happens in this case? If we consider the first one, we have this result. But let's take a look at what happens here at the intersection of the two faces. In one case, one of the normals will go out, the other one will go in. Remember, if we consider one surface, this surface gave rise to the product fy x y plus dy z times 1. But if we consider the other one, the normal is pointing outwards and the vector is pointing inwards, so we get a minus sign. So on this face, this term will not contribute. So the intersections of surfaces will not give rise to any contribution. The thing that gives contribution is the elements on the surface that we are going to integrate. The contributions of these cubes are important only in the external surface. Okay, so if you consider a surface, a very big surface, but a closed surface, the surfaces of those cubes that give contributions are only the surfaces that are contained in the surface of the entire volume that we have to integrate over. So in this case, this is volume V. We have these very small cubes that give rise to some contributions. We have this cube. I hope you get the idea. So this is the important part of the cube that gives rise to contributions. So in general, if we consider a single cubes and then sum over all the cubes, we can get the surface, the integral over the surface. So in general, I can just integrate here and then we get the final result. In here, I can put the boundary of the volume, which is the surface, and then integrate over the volume. So I hope you get the idea. This is a bit tricky, but I will try to explain it a little bit better to conclude this video. When we integrate over the cube, we can sum over all the cubes to obtain the surface, and we obtain the integral over the surface, the internal contributions are zero, because there are faces which have opposite normals, and these normals give no contribution. So the contribution that are important are only those on those parts of the cubes that also lie on the surface that encloses the volume V.